All right, guys, so we're still pushing along through 4.2, the mean value theorem. It is a little bit of lengthy of a section and a topic, but mainly because the mean value theorem is it's very important. I think it's at some point, I think it kind of gets to be a little more common sense than anything. We can utilize it in a lot of different, ways. We've talked about how to utilize it a little more in application, algebraically. We talked in the last video in regards to how can we almost kind of, physically interpret it and using that car example that we had talked about. And now let's kind of look for a second as to one of the main uses of it, and it's the mean value theorem and its use in application with increasing and decreasing functions specifically. So our mini goal for this video, amongst the big goal of the entire section, is to use the mean value theorem to show functions increasing or decreasing over a given interval. So let's think for a second what it means to be increasing and decreasing. So I'm not going to waste too much time on this. I think you guys can all and everyone can understand what happens when a value is increasing or decreasing. If, let's say we have a graph, all right, let's say we have a graph right here, and we're dealing with an increasing function. If you have a point x1 and a point x2 right here, the function is going to be considered increasing if the value, if x1 is less than x2, but the value specifically of fx1 is still less than f of x2, because this value f of x1 is less than wherever the value of f of x2 comes into play. So this is considered an increasing function. And then it goes vice versa. Let's say, for instance, we're dealing with decreasing functions. We have a decreasing function. Let's say in this case we are dealing with, once again, x1 and x2, but let's say the function looks more so like this in this particular example. So here we can see that x1 is still less than x2, but the value for f of x1 is now greater than the value for f of x1 is greater than the value of f of x2. So that shows a decreasing, and this showed an increasing function up top. And so that's kind of hopefully a little more common knowledge for us. Where the mean value theorem has a corollary that's very interesting is when we start dealing with derivatives. So our corollary, or additional statement, is all corollary really means. So let f be let's just say continuous. Let f be continuous, us, on the closed interval ab, and once again make sure that it is differentiable on the open interval ab, just like it was for our mean value theorem. All we're doing is basically just rewriting the mean value theorem starting point to start off with. If this is the case, we have these circumstances happen, then the first thing that happens that is if the derivative of f is greater than 0 at each point of the open interval AB, then we can for sure say that f increases on the closed interval a to b. And then on the second hand, if f prime is less than 0 at each point of the open interval, guess where our differentiable is the open interval, then we can say f decreases on the closed interval AB. So what this basically tells us, guys, is that we can use the derivative to define whether it is increasing or decreasing, and this shouldn't be new to us. This is exactly what we did when we graphed derivatives of a function. We know that if f prime is greater than 0, then that shows increasing from the function. If f prime was less than 0, then we showed that it was decreasing on the function. We just did it in reverse order. We were saying, hey, where is f increasing? That's where we're going to have a positive derivative. And then we said, where is f decreasing? That's where we're going to have a negative derivative. And so that's exactly what this is kind of reiterating for us specifically. So let's say for an example, we're looking at our first example of the day, and we just want to determine where specifically is the graph going to actually where the graph is actually going to rise and fall. So let's look here for a sec. We have our example. It says determine where the function will increase and decrease. Our function that we are dealing with specifically here is y equals x squared. So very, very simple, and let's take a look. We know that our graph for y equals x squared, something of the nature that goes through here. And so we just got to kind of look for a second what's happening. So let's go ahead and just take care of the decreasing side of things here first. So we know that the function is going to be decreasing all from negative infinity all the way to 0. So yes, you can look at that and just say we know it's decreasing from negative infinity to 0. But think about what it means to be the derivative. Y prime is 2x in this case. The derivative of y is 2x. 2x is always going to be less than 0 everywhere from negative infinity to 0, because negative times 2 is always going to give us a negative value. So we know that it's going to be decreasing because the derivative is always going to be less than 0 from negative infinity to 0. And then from the increasing side of things, so we know it's going to be y prime equals 2x will be greater than 0 as long as x is positive. As long as x is positive, we know that we are going to have, let me change colors actually here. We know as long as x is positive that we are going to have a positive derivative. So everywhere, specifically on the open interval from 0 on to positive infinity, we are going to have increasing in this case right here. Well, let's look at a little bit more interesting function in this particular example that we're in the topic that we're dealing with. Let's say for, and of course I'm getting kicked out again. I apologize, guys. I have no idea what's been going on with OneNote lately, but it kicks me out all the time. So give me a second to get this loaded back on up. Whenever you get to this point, you can just fast forward through when you get on the video when I have it back on up. All right, guys, we should be back up and running again. So let's take a look at more of an interesting example for this case. Same thing goes. I want us to go ahead and find where it is increasing and decreasing. So where increasing and decreasing. Let's look at more of an interesting function this time. Let's say we are dealing with the function f of x equals x cubed minus 4x. Once again, we want to find out where it's increasing and where it is decreasing. Well, of course, we can look at it graphically. Let's say graphically is not an option for us in this particular case. That means we need to know where the derivative is greater than 0 and where the derivative is less than 0. Because if f prime of x is going to be, this case, 3x squared minus 4, if this is going to be greater than 0, that means we're going to see an increasing part of the graph. So let's find out what the x value is when it is specifically greater than 0. So it's going to be increasing when it is greater than 0. So let's find out what that x value is. So 3x squared is greater than 4 in this example. And then you're going to see that x squared is greater than 3. And then taking the square root, you get, is 4 over 3. 4 over 3. And then the square root is going to be x. Now, remember, don't forget, guys, you got that plus or minus that comes into play here. So it's less than the negative of square root 4 over 3, and then x is greater than the positive of 4 over 3 because they have that positive and the plus or minus that comes into play as well too. So when x is less than negative square root 4 over 3, it's going to be an increasing interval. Or when x is greater than square root of 4 over 3, it is also going to be an increasing interval here. So increase and increase amongst those two spots. And then let's go ahead and say, well, we need to find out when it's decreasing. So 3x squared minus 4 is less than 0 when it is decreasing. So doing the exact same concept here, you're going to see that x squared is less than 4 over 3. And when you square root both sides, in this case, you still have to take into account your plus and your minus. But because it is dealing with less than, it would be greater than the negative portion of things. X would be greater than the negative portion of things. And then x would be less than the positive portion of things. So this is when it's going to be decreasing. Once again, guys, let's kind of go back and hear how these square roots ended up working out. Because of the square root of this top function right here, took the square root of this top function right here, because that is a plus or minus, when it was less than, that's the opposite, right? That's when it would be negative of the square root. And because it was positive originally, it was greater than originally, that's when it's the positive side of things. Because down here at the bottom, we have it less than 4/3. That means the opposite means x has to be greater than it. And then the positive says that it'll be less than it. So those are the two spots where it's increasing and then where it's decreasing. So let's put this in interval notation. So it is increasing in interval notation specifically from negative infinity to negative 4, square root 4 over 3, right? And that's going to be included because that's what we're dealing with, it included. And then it goes and decreases, right? It decreases, including, right in between, square root of 4 over 3 and positive square root of 4 over 3. Once again, including. And then it goes and increases once again. In this case, we were going from the opposite side of things. So when it was positive square root of 4 over 3 onto positive infinity here, okay? So there's kind of a last little look into our mean value theorem in regards to increasing and decreasing functions themselves.